All right, so now let's look at the next concept, which is about absolute max and mean for functions. So let's start with the definition of absolute max and mean. Let f of x be a function with domain, let's say df. We say that x equals a, but inside domain of f is an absolute max for f of x if f of a is bigger than or equal to f of x for every x inside domain of f. If f of a is the largest value compared to all f of x values for any x inside domain, then we say x equals a is the absolute max for the function. Similarly, x equals a inside domain is called an absolute mean. Absolute mean for f of x if f of a is the smallest value compared to all values inside the domain. So let's look at this graph of a function like this. Let's say like this, for example. Let's say this is, for example, 1. Let's say this is 2. This one 4, this one 5. So the domain of this function is 1 to 5, right? So this is, let's say, y equals f of x, and domain is 1 to 5. Now, does this function have absolute max or absolute mean? Well, absolute max means the value, the x value for which the output is the largest compared to all outputs of the function. But when we look at the graph of this function, this output here is the largest compared to all outputs of the function. All right, so this value here, the y value, is some number. We don't know exactly how much because it's not given, but it's definitely largest compared to all other outputs. It's bigger than f of 1, bigger than f of 1.5, 2.5, f of 5. F of 2 is the biggest one. So we can say that f of 2 is bigger than or equal to f of x for every x inside domain. So that means x equals 2 is absolute max. Similarly, which output is the smallest output among all outputs of this function? Well, again, obviously, f of 1 here, f of 1 is the smallest output compared to all other outputs. F of 1 is smaller than f of 1.5 or 2 or 2.5 or any other output for the function. So we can say f of 1 is less than or equal to f of x for every x in the domain of f, and that means x equals 1 is absolute mean. So now the question here is, I want to ask a question. Can we say that an absolute max is always a local max? Similarly, can we say an absolute mean is always a local mean? The answer is no. See, you may think about absolute max means largest in the whole domain. Local max means just largest locally around the point. But if it's largest in the whole domain, it has to be largest locally around the point as well. That's almost true, but not if the point is an end point. If the point is an end point of the domain, because for local max, we need the function to be defined around that point. Around means left and right side of the point, both of them. And then it has the output has to be locally largest in that interval. But if absolute max is an end point, then the function is not defined around that point at the left and right of that point. So in that case, absolute max will not be a local max. But otherwise, if the absolute max is not an endpoint, then it will be a local max as well. So in general, if I want to say in general, the answer is no, since if an absolute max is an endpoint, then the function is not defined both sides of that point, and therefore no local max. Similar situation for local mean. So let's look at an example. Let's look at a simple example. F of x equals x on 0 to 1. This is the graph of the function. So here, of course, we have absolute mean at x equals 0 and absolute max at x equals 1. But again, absolute mean at x equals 0 will not be a local minimum. X equals 0, not a local minimum, since there is no open interval containing, there's no open interval inside domain that contains 0. Contains x equals 0. You have to go back and look at the definition of local max and mean. For local max and mean, we need an open interval containing the point. An open interval inside the domain. Here the domain is closed interval 0 to 1. So what type of open intervals contain 0? Well, if the open interval is from 0 to somewhere, it will not contain 0, because if it's open 0 to something, then it won't contain 0. If you want an open interval to contain 0, it needs to start before 0. So minus point something, for example, to some positive number. An open interval containing 0 must be defined on start from before 0 and end after 0. But before 0, if you want to start before 0, domain starts right from 0. So before 0, there is no point of the domain. So any interval of the form minus something or minus point something to a positive number will not be in the domain. I need an open interval inside domain that contains 0. There is no such open interval. So that means x equals 0 is not local mean, although it's absolute mean. Because for absolute mean, I do not have such a requirement that an open interval must contain the point. There is no such requirement for absolute mean. But for local mean, we have that requirement. Therefore, this point is absolute mean, but not local mean. Similarly, x equals 1 is an absolute max, but not a local max. Now, another question I can ask here is if absolute max and mean, max or mean exists, can we say it is unique? Let's say if we have a function that has absolute max and mean. Does it have to be one absolute max and one absolute mean? Or can we have, for example, 2 absolute max, 2 absolute mean, or even 5 absolute max, 6 absolute mean, for example? Is that possible? It is possible. So the answer is no, it doesn't have to be unique. Construct an example verifying this fact. So please construct an example of a function that has more than one absolute max or mean, or maybe both. Okay, next question I want to ask is that which functions, or for which functions can we guarantee the existence of absolute max and mean? Remember, for functions, local max and mean may or may not exist depending on the function. Similar situation for absolute max and mean, may or may not exist. But for certain types of functions, we have a guarantee for existence of absolute max and mean. You want to know for which type of functions can we guarantee existence of absolute max and mean. So this is the answer to this question is given by a famous theorem called extreme value theorem. So the answer is if the function, or for the functions, for functions that are continuous and defined on a closed finite interval. Okay, for these types of functions, we have guarantee for existence of absolute max and mean. Now let me state this as a theorem to see below. This theorem is called extreme value theorem. It's a very important and fundamental theorem in calculus and in analysis. So it says that let f be a function, be a continuous function defined on a closed finite interval say A to B, then f of x takes its absolute max and f of x takes its absolute mean. Okay, a simple example for this theorem. For example, let's say f of x equals x, a very simple continuous function on a very simple closed finite interval, say 0 to 1. Then f of x takes absolute max and mean, right? So this is the function we also saw above. Then we saw that x equals 0 is absolute mean. Absolute mean for f of x, and x equals 1 is absolute max for f of x. All right. Now one example, show that the conditions above in extreme value theorem cannot be removed. See, in mathematics, we always prefer to have as little as assumptions as possible when we deal with a theorem. So if some assumptions can be removed and still the conclusion holds, of course, we prefer to do that. But here we made two assumptions. The fact that the assumption that f is a continuous function, and the second assumption is that the domain is closed finite interval. Now, if I remove any of these two conditions, assumptions, then the theorem will not be valid anymore, which means that both conditions, assumptions are really required. I cannot remove these assumptions. So how can I show this? I can show with examples that because, for example, I want to show that the continuity of f is required. I cannot eliminate it or remove it. So I can give an example of a function which is not continuous and it doesn't have absolute max and mean. That means if I remove the condition of continuity, then the theorem will not be valid anymore because it may not have absolute max or mean once I remove the condition. So the example showing that continuity is required. Let's look at this example first. Let's say if I define f of x equals, let's say 1 over x, for x not equal to 0 and 0 if x equals 0. Okay, now let's consider f of x on some closed finite interval, let's say 0 to 1. Then f of x has no absolute max. Why? Because when we look at the limit f of x as x approaches to 0 from right, if x is a little bit bigger than 0, then the formula for f of x will be 1 over x, and limit 1 over x, x approaches to 0 plus is infinity. So that means the value of function will get bigger and bigger, arbitrarily big, as x gets closer and closer to 0 from right. So that means there is no absolute max. There is no largest output because the values will get bigger and bigger. There is no largest output for f of x, and therefore f of x has no absolute max. Okay, so this example shows that the continuity of f is required. This function is, of course, discontinuous, and it has no absolute max. So look at the theorem. The theorem says if the function is continuous and defined on a closed finite interval, then f of x will take absolute max and will take absolute mean. But I just give an example of a function f where it was defined on a closed finite interval, but it wasn't continuous, and absolute max did not exist. So this condition is really needed, is really required. If I remove it, the theorem will not be valid anymore. Now, the next example, the example that shows the interval being closed finite is required. Example that shows the second assumption. Closed finite interval cannot be removed. For this one, let's consider f of x equals x. Very simple function. It is continuous, but this one, let's say on interval 0 to 1, open interval 0 to 1. Then f of x does not take absolute minimum, nor it takes absolute maximum. To show f of x does not take absolute minimum, let me do use it, prove it by contradiction. By contradiction, suppose that f of x takes absolute mean at, let's say, some x equals c. I want to show it doesn't take absolute mean at any point, but let's say it takes absolute mean at x equals c. Of course, absolute mean has to be inside the domain, remember. Absolute max and mean, by definition, they must be in the domain. So let's say some value c is the absolute mean. So what does that mean? That means f of c must be the smallest output among all the outputs that I have. Look at f of x equals x between 0 to 1. The interval is open, so it doesn't contain 0, doesn't contain 1. And I'm assuming that there is some c that is the smallest f of c, which is c as well, is the smallest output. Well, is that possible? That is not possible. It's not possible that c is the smallest output, because I can give an explicit number with a smaller output compared to c. And that explicit number is, well, some people say, for example, c minus something. Say c minus 0.1, for example. I cannot make such argument because I don't have any information about c. If you say c minus some number, for example, c minus 0.1 or c minus 0.01, you may you may go outside of the domain, because the domain is just 0 to 1, right? So let's say, for example, you say c minus 0.1, but c itself is less than 0.1, for example, 0.01. then c minus 0.1 will be outside of the domain. Okay, so we want to find another point inside the domain whose output is smaller than c. That number will be c over 2. And note f of c over 2. F of x is x, so f of c over 2 is c over 2, which is less than c, since c is bigger than 0. C is between 0 to 1, so bigger than 0. If a number is bigger than 0, c over 2 will be less than c. And this is contradiction with, remember I had to have f of c. I was supposed to have f of c being the least number among all the outputs. F of c must be f of c, which is c. This c here is f of c. F of c, which is c, must be the least output compared to all outputs. But I just found another output, f of c over 2, which is c over 2, which is less than c. Okay. So that means f of x has no absolute mean. Similarly, show that f of x has no absolute max. Okay, so if the domain is not closed finite interval, then the function may not have absolute max and may not have absolute mean. Of course, it may have absolute max and it may have absolute mean as well. Okay, so you can think about an example of a function that the domain is not closed finite. Let's say if the domain is open finite interval, or maybe open infinite interval, and the function still has absolute max or still has absolute mean. That is possible. And it is also possible that it doesn't have absolute max and mean. In other words, we won't have a guarantee, because it's all about guarantee. When can I guarantee existence of absolute max and mean? Only if existence of absolute max and mean can be guaranteed only if the function is continuous and the domain is closed finite interval. Let's say closed interval a to b. Okay, so these examples verified this. Now the next question is, okay, we learned when we can have guarantees for existence of absolute max and mean. But let's say we have a guarantee for existence of absolute max and mean. Now the next question is, how can we find it? So assuming f of x has absolute max and mean, how can we find absolute max and mean? So to answer this question, we need a fact. Let domain of f be equal to, let's say, closed interval a to b, if absolute max and mean, max or mean, does not occur at an endpoint meaning that does not occur at x equals a or x equals b, then f of x has a local max or mean at that point. And hence that point will be a critical point for f of x. Okay, so the absolute max and mean, if they exist, they occur either as an endpoint or as an interior point. If they occur as an interior point, they will be local max and mean as well. Why? So proof of fact. Let's say suppose that x equals c belongs to, let's say, open interval a to b is an absolute max for f of x. Okay, so the fact says if absolute max and mean does not occur as an endpoint. So let's say if x equals c is an absolute max and not an endpoint. If it's not an endpoint, means it's not a, not b, then where will it be? Well, it will be inside the open interval a to b, right? Because I'm assuming domain is closed interval a to b, and if c is not a, not b, it has to be inside open interval a to b. So then, first of all, I want to say that there will be an open interval containing c. Then there exists I inside domain such that open interval, let's say, such that there exists an open interval I inside domain such that C belongs to I. Check this. See, let me show you the picture. So this is A, this is B, C somewhere here. I'm saying that if C is inside a interior point of A and B, strictly between A to B, then there will be some open interval like I containing C. So please try to verify this. Why can we say that there exists an open interval I that includes C? What will be that open interval? Can you express it explicitly or at least prove its existence of such an open interval? Try to verify this. And then the exam open interval I such as C belongs to I. And so that's one condition for local max. And the other condition is that the f of C must be biggest output compared to all outputs inside I. But because C is absolute max, f of C is biggest output compared to all outputs of the domain. And of course, compared to all outputs inside I as well, right? So the other condition will be valid automatically. So we have f of C is the biggest one compared to all outputs inside the domain A to B. So that means f of C must be the biggest output compared to all outputs coming from the interval I, because interval I was inside closed interval A to B. And that means x equals C is a local max, local max. And similar argument, of course, holds for local mean. All right, so for local max, we show that if a number is absolute max, then it will be local max, as long as the number is not an endpoint. Similarly, if you have absolute mean, which is not an endpoint, it will be local mean. And therefore, we know that if we have local max and local mean, or local mean, those points must be critical points. So this fact says, if you have an absolute max, which is not an endpoint, then it must be a critical point. So what will be the potential absolute max and mean? What will be the candidates for absolute max and mean then? So based on this fact, based on the fact above, the candidates for absolute max and mean for a continuous function defined on, let's say, closed finite interval a to b are as follows. So what are the possibilities? Of course, one possibility is endpoints. It is possible that absolute max or mean occur as an endpoint. For local max and mean, no. According to the definition, local max or mean cannot occur as an endpoint. But absolute max and mean is okay, are okay to occur as an endpoint. So that's one possibility. The other possibility, if absolute max and max or mean do not occur as endpoint, according to the fact, they must be critical points. That's exactly what the fact said, right? The fact said if absolute max and mean are not endpoint, it is possible that they are endpoints. Endpoints are absolute max and mean. That is possible. But if endpoints are not absolute max or mean, then the absolute max and mean must be local max and mean, and therefore critical points. Okay, so the second possibility is critical points. And once you collect all points given by 1 and 2 above to decide which one or which ones is or are absolute max or mean, compare the corresponding outputs. The largest output gives the absolute max. The smallest output gives the absolute mean. Okay. So for absolute, if you have a function which is continuous and defined in closed finite interval, the extreme value theorem that we mentioned above guarantees existence of absolute max and mean. Now that we know about the existence of absolute max and mean, then the question is how to find it. But if you want to find them, you have to consider different possibilities. One possibility is that they occur as an endpoint. Another possibility is that they don't occur as an endpoint. If they don't occur as an endpoint, the fact above said that, then they must be critical points. So once you collect all the endpoints, where you have only 2 of them, A and B, and all the critical points, then these are the candidates. Therefore, absolute max must be one of these points. Absolute mean must be one of these points as well. How can we decide? Well, just find the outputs, because remember, absolute max is a number that the output corresponding to that number C is the biggest one compared to all outputs in the domain. Well, therefore, I just need to find the outputs corresponding to these values that I find in 1 and 2 here. And the biggest output will give me absolute max. The smallest output will give me absolute mean. Okay, so let me show this in an example. Find the absolute max and mean of, let's say, f of x equals x squared minus 2x plus 8 on the interval, let's say 0 to 3. See, this function here is a continuous function. Of course, the polynomial and the domain is closed finite interval. So it must have absolute max and mean. The question is not asking us to verify existence of absolute max and mean. It just asks us to find it. How can I find it? I have to follow this algorithm. To find the absolute max and mean, just find the endpoints, critical points, and then compare the outputs. It's very simple. So what are the endpoints? So solution, endpoints, x equals 0, x equals 3, just 2 endpoints. Critical points. For critical points, I need to solve for f prime of x equals 0. That gives me 2x minus 2 equals 0. And that gives me x equals 1. So then we have to compare, okay? Don't compare the x values, compare the y values corresponding to these 3x values. So we have to compare f of 0, f of 3, and f of 1. And then see which one is the largest one, which one is the smallest one. F of 0 is 8, obviously. F of 1 is 9 minus 2, which is 7. And f of 3 is 9 plus 8, 17, minus 6, that's 11. Now, which one is the largest one? 11 is the largest one. That means absolute max is x equals 3. Because absolute max and mean are defined as the x values, not the y values. Y values are called absolute max value or absolute mean value. If they ask for absolute max value, that's 11. Absolute max is x equals 3. What about absolute mean? Which one is the smallest one? This one is the smallest one between 8, 11, and 7. 7 is the smallest one. So that means the absolute mean will be x equals 1. All right, that's it. So absolute max x equals 3, absolute mean x equals 1. Let's look at another example. Example, find the absolute max and mean of f of x equals 2x cubed minus 15x squared plus 36x on the interval 1 to 5. Okay, so again, it's very straightforward. I just need to find the candidates, which are the endpoints and the critical points. Please note that again, here we have a continuous function defined on the closed finite interval. Therefore, it must have absolute max and it must have absolute mean. It's just how to find them. And to find them, we just need to follow the algorithm. So basically the candidates here are endpoints. X equals 1 and x equals 3. And also the critical points. For critical points, I need to solve for f prime of x equals 0. Prime of x equals 0, that will give me 6x squared minus 30x plus 36 equals 0. So if I take 6 out, x squared minus 5x plus 6 equals 0. That gives me 6 times x minus 3 times x minus 2 equals 0. And that gives me x equals 3 and x equals 2. And x equals 3 was already included above. I don't need to include it twice. And this one is an additional point. So please here note that in the step 2 where you find critical points, so it's basically 2 steps. Endpoints, just look at the interval, and critical points. For step 2, which is finding critical points, you have to only include critical points inside the domain. If for example, here in the critical points, let's say if I had, for example, 5 as another critical point. Oh, sorry, the interval is 1 to 5, not 1 to 3. So the endpoints are 1 and 5, and critical points are 2 and 3. So 3 is not included above. I have to erase this sentence. So what I was saying was that the critical points must be inside the interval. So the interval here is 1 to 5. So let's say if another critical point I had, for example, 6. If I had 6 as a critical point, I should reject it. Because 6 is not inside 1 to 5. So we only accept critical points which are inside our interval. Maybe I can write as a note, only accept critical points that are inside the interval 1 to 5. That are inside your interval, let me see, or that are inside the domain. In this case, 1 to 5. Okay, then lastly, we need to compare the outputs. Which outputs do I need to compare? F of endpoints, which means f of 1, f of 5, and f of critical points, f of 2 and f of 3. Compare them, see which one is the largest one, which one is the smallest one. Let's calculate them first. We have the formula for f of x, right? F of x is this, so you can easily find f of 1 or f of 5 or f of 2 or f of 3. F of 1, you can see it's 23. F of 5, you can calculate, you will see it's 55. F of 2, it will be 28. F of 3 will be 27. So which one is the smallest one? The smallest one is 23. And this gives me the absolute mean. So absolute mean will be the corresponding x value, which is 1. Absolute mean and max must be the x value. And the largest one here is 55 as the output. For absolute max, I need the x value. X value will be 5. 55 corresponds to 5. F of 5 is 55. So this is the largest one, and that gives me absolute max of x equals 5. Okay, guys, so we saw about the definition and the definition of absolute max and mean, and the comparison with local max and mean. When can we say absolute max and mean is local max and mean? And which functions are guaranteed to have absolute max and mean? The continuous function, defined and closed finite interval. And if a function has absolute max and min, how can we find them? And the algorithm was very simple. Just find the endpoints, critical points, and then compare f of endpoints and f of critical points to determine which point is absolute max and which point is absolute min. Okay, guys, so thank you and see you next time.